So 1, 2, 3, 4. 4 methyl, 1, 2, 3, 4, 5. 2 pentanol. 4 methyl, 2 pentanol. Or pentan 2-O. Now the second one is this. You have CH3, 3OH. We are asked to give the IUPAC name for this. So first, this is a condensed structure of an alcohol, so we have to open it. So this is my carbon. They say there are three methyl group attached to it. So here will be 1, here will be 2, here will be 3. This is my OH here. So if you look at this structure, this is not position 1. By looking at it, you know that this is either 1, 2, 3, or 1, 2, 3, or 1, 2, 3, as the case may be. Maybe we should take it straight up this way as 1, 2, and 3. So if this is our 3, our parent chain is our propane backbone. So we have 2 methyl propan 2-O. Two methyl propan 2-O, or 2 methyl 2-propanol. Let's take another one, which is CH3, CH2. Now, this is it. Now, let's write our structure down. This C has hydrogen and OH, so this is my OH. I move to C, this one has hydrogen and chlorine. And this is C, H3. So it's obvious that we come from here 1, 2, 3. 1, 2, 3. The OH is in the middle, but we give preference to this side because the total number of locants will be lower. 2 plus 3 is 5. 3 plus 4 is 7. So we come from here. So this is 1, 2, 3, 4, 5. So if it is 5, this is 2-chloro pentan 3-O. 2-chloro pentan 3-O. Because the OH is in the third carbon atom. Or 2-chloro 3-pentanol. Let's take one more, then we'll go to the preparations. Let's start. This is my first carbon here, and they say I should write 3 of CH2. 1, 2, 3. And I'm in this carbon, which is this carbon. This carbon is having 2 CH3, 2 CH3, and OH. This is exactly what is in the last carbon. There are CH3, 2 of them attached to this carbon and 1 OH. So it doesn't matter if you put this OH here and this here, it doesn't matter. Okay, this can be our terminal carbon, this can be our terminal carbon. Even if we have CH2 here, it could be our terminal carbon, so it doesn't matter. So from here, we come from this direction. Obviously, here, 1, 2, 3, 4, 5, 6. So it's a zinc. There's an O. So we have 2 methyl, 2 methyl hexane 2-O. Okay, 2 carbon 2, we have a methyl and the OH is in carbon 2. So it is 2 methyl hexane 2 or 2 methyl 2 hexanol. Alright. Now let's write more, just few more. Okay, let's take this. CH2 H CH2 So here I have my C, which has 2 hydrogen and 1 OH, and another C that have 2 hydrogen. Let me put the hydrogen beside, and 1 OH. So this is 1,2 ethane diol, or ethane 1,2 diol. Ethane 1,2 diol. Okay. Let's write the structural formula of the following. 2-bromo, 3-methyl butane, 3-methyl butane, 2-ol. So our parent chain first is the butane. So they have given us butane. 1, 2, 3, 4. Butane 2-ol. So OH is in carbon 2. From here, that is what it means. Then 2-bromo will also be here. Bromine will be here. 3-methyl, 1, 2, 3. Yeah, CH3. So this is 2-bromo, 3-methyl, 2-butanol, or butane 2-ol. So that is just it. They say we should write the structural formula of that. Now the next one is this. 3-ethyl, 2,5-dimethyl, dimethyl 3-hexanol. Hexanol. Okay, 6. 1, 2, 3, 4, 5, 6. It's a 3-hexanol. Means our OH is in carbon 3. 3-hexanol. Let's begin. 1, 2, 3, 4, 5, 6. 1, 2, 3. That's what our OH is. 3-hexanol. So now we start. 3-ethyl. 1, 2, 3. This is ethyl. It's in carbon 2. We have CH2, CH3. 3-ethyl. 2,5-dimethyl CH3. 1, 2, 3, 4, 5. CH3. Okay, from there, this is it. Okay, now E comes before N. So that is why it is 3-ethyl, 2,5-dimethyl, 3-hexanol. So let's take another name. Another one is 3. Okay, I just said that. 2-chloro, 1,4, 2-chloro, 1,4, but 2-N-diol, 1,4, but 2-N-diol. Alright, there's a double bond here. Now, but is butane. 1, 2, 3, 4. So but 2 means it's in carbon 2. The double bond is in carbon 2. Okay. Now 2-chloro, this is my chlorine. 2-chloro, 1,4. The 1,4 is the OH group because it's diol. 1,4. Put 2N diol. That is it. So now let's name it now. 1, 2, 3, 4. So our chlorine comes first. 2-chloro, 1, 4. Put 2 N diol. So the technicality is always there, but we must pay attention to it so that we don't make mistakes. If you remember the rules, you will understand what we do. So let's move on to another question. A secondary alcohol is the alcohol where the carbon carrying the OH group is attached to 2 other carbon atoms. So let's start. Let's see. CH33 OH. That is 1. This one is CH3 CH OH CH3. Here is CH2OH. And CH2OH. And the last one is CH3 2 CH CH2OH. So let's find out which of them is a secondary alcohol. Which of the following is a secondary alcohol? Let's start with this first one. The first one is we have 3 CH3. CH3. Okay. I don't know what they want there. That thing doesn't look clean to me. CH3, 3 of them. Where are they bonded to? There's supposed to be something like CH3. So I think this is what they mean. CH3, CH3, CH3. Then this is our OH. So there are 3 CH3 and OH. So this is a tertiary alcohol. So that one is out. It's not that. The second one is CH3, 1. This C contains 1 hydrogen and 1 OH, and there is a CH3. This carbon is bonded to 2 other carbon atoms. This is correct. Let's just check the other one. This is COH, OH. This is primary. From this carbon is primary, this carbon is primary, so this is out. And this one, CH3, there are 2 CH3 bonded to this. Good. So we have this carbon here having CH3, CH3, and hydrogen. Then it's bonded to another carbon having hydrogen, OH. This carbon is primary, this one is tertiary, and this one is primary. There's no secondary. So this is our correct answer. So let's take another question. By the use of an alkanol with 4 carbon atoms, draw one structure each to illustrate the primary, secondary, and the tertiary alkanol. So we should make use of an alkanol which has 4 carbon atoms, that is butanol. We use it to illustrate primary, secondary, and tertiary alkanol. So this is 1, 2, 3, 4. 1, 2, 3, 4 OH. So We want to use that to illustrate our primary. So let's take this to our first one butanol. This is our primary. 1, 2, 3, 4 carbon atom. This is our tertiary. Yes. Yeah, this is our tertiary, and the last 1, 2, 3, 4. And this is our secondary. Primary, secondary, and tertiary. Now let's go down to preparation of alkanols. How can we prepare alkanols? We have the alkaline hydrolysis of haloalkanes. We say this reaction can be achieved by refluxing the haloalkane with an aqueous solution of sodium or potassium hydroxide. So let's say chloromethane plus sodium hydroxide, CH3Cl plus sodium hydroxide. What's the condition? We have 100% here, 100 degree, and water. That should be 100 degrees Celsius, the temperature. So from here, we'll be able to prepare what? Alcohols. So what happened? The Na, the metal, will take out this to give us sodium chloride, and the OH will replace it. So we now have CH3OH plus sodium chloride, aqueous. Okay. So with that, we've been able to produce our methanol, which is our first method of preparing what alkanol, say alkaline hydrolysis of haloalkanes. Now the next one is hydration of alkenes to add water to what? Alkenes. I will show us the mechanism. Hydration of alkenes. Now, hydration of alkenes, we have C double bond C, which is 18, plus hydrogen hydroxide. What is the condition? Hydration, using hydration of alkenes, H2SO4 and water as a catalyst, which is, this is the water, so I don't need to put that, in the presence of an acid. Now, when we're dealing with alkenes, we talked about, how do I call it, in the halogenations, where halogens react with alkenes to form halo compounds. How did that happen? The chemistry, I explained it earlier on, how this will be able to break in to feed into these two guys. That's in the mechanism. But then let me show you what happened right now. So I will proceed further. So this will give us C double bond. It will break the carbon atom to give us OH, which is ethanol. Now, you know our CH3 hydrogen. Now let me show us the mechanism. How does that happen? This is C double bond C plus hydrogen double give us this. So this will move to here to give out its bond, and this will also give out its own bond. And we have carbon which is plus, it has given out. We have another carbon which is negative. It is now looking for another to balance that. So this is in excess. Then plus hydrogen which has given out become positive, plus the OH which has received becomes negative. And in chemistry or in physics or in science generally, we've been told that positive charge attracts to the negative. Okay, the positive attracts the negative. Unlike charges attract, similar charges repel. So it means that for these two to bond together, the positive will come to the negative, yeah? and the negative will come to the positive, as the case may be. So this, if this OH come over here, this gives me my OH, and this is my carbon, which is negative, it takes the positive, so this becomes my hydrogen. So remember, there were two hydrogens here. Don't forget that, even when I don't put them. These two hydrogens are there already. So this side I put my two hydrogens that were there, and this side I put my other two hydrogens that were there. This is ethanol. So this is the mechanism that takes place to give us that ethanol. So in a longer chain of an alkene, the position of the water molecule coming into the alkene group depends on where the double bond is. You don't just bring it and put it anywhere you like. It has to go to where the double bond is, because that is where the chemistry is taking place. You have to take note of that. So let's move on. We are still under the preparation of alkanols. This is what hydration of alkenes. The product in the hydration of the alkene below. This is 1, 2, 3, 4, 5. Okay. Okay, like I was saying earlier on, this OH and hydrogen will come into this, but not anywhere. You can't put it here. It has to come to where the double bond is. That is where it will come directly. And it depends on the movement of the bond movement. If it moves to this side, this becomes negatively charged. The OH will come to the positive and the hydrogen will come to the negative, as the case may be. So for this, let's just put the arrow down in the presence of an acid. Excuse me. Now we have carbon there. This carbon will take, one of it will take the OH group, and one of it will take the hydrogen. Then we move on to carbon, and carbon. So this is what we get. Is it 6 or 5? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that becomes 2-pentanol. This is where it will be. 2-pentanol. So another method which we can prepare alcohols is through fermentation. Okay, let's look into it. I'll read that for us. It says fermentation is the breakdown of complex carbohydrate by the action of enzymes to produce ethanol and carbon 4 oxide. And we know that an enzyme is a natural organic catalyst secreted by living cells. They are proteinous. Okay, enzymes are catalysts and they are proteinous in nature. Now, the fundamental reaction underlying the production of ethanol by fermentation is the catalytic conversion of glucose into ethanol by enzyme called Z-mase, which is present in yeast. The process is exothermic. That is, we have our glucose, C6H12O6, and that's in the presence of Z-mase, it gives us our ethanol plus carbon 4 oxide plus heat. Now, through this fermentation process, we can produce wine from ethanol. Okay, we can produce wine from ethanol. So let me just give you the procedure. The preparation of that ethanol in the lab, I will have it covered in one of my classes where we are going to use fermented palm wine to produce our local gin, right, which is 95% ethanol, and that is very powerful. So let's go and see the process of doing that. We say palm wine occurs naturally in oil palm trees as a white liquid. For those of you who drink, you know what palm wine is. It's whitish. Its white color is due to the fact that it contains yeast. That's why it's white. while its natural sweetness shows that it contains a high concentration of glucose. Because of that glucose present in it, it makes it very sweet. When fresh palm wine is allowed to stand or kept for 3 days, when you keep it for a long time, for 3 days, enzyme Zymes in the yeast ferment, so fermentation will start. And when it ferments, the glucose to ethanol with the evolution of carbon 4 oxide will be formed. Okay, the enzyme Zymes in the yeast ferments the glucose, okay, to ethanol with evolution of carbon 4 oxide. This explains why fresh palm wine fruit, you will say it's fruiting. When the mixture is distilled after that fermentation, we distill it. It's called illicit gin, which is popularly called ogogoro in Nigeria. So what I'm saying simply, you get your fresh palm wine, you allow it to stand for 3 days, you cover it, it will ferment. Okay, when after the fermentation, we now distill the product therein. After distilling it, we get what we call ogogoro, which is the name we give it here in Nigeria, West Africa. Now let's look at the chemical reactions of ethanol. Ethanol reacts. All right, let's see. Now alkanols or ethanols are generally reactive. Their reactivity is due to the possession of hydroxy group. The presence of the hydroxy group in it makes it reactive. The following reactions of ethanol are typical of alkanols. One is combustion. Ethanol burns with blue, non-luminous flame to give carbon 4 oxide and water vapor. The reaction is exothermic. Okay, let's take an example of ethanol plus oxygen. Okay, so now we have to balance it. We say we're having carbon 4 oxides and water plus heat, perhaps. It is required because this sample, it is exothermic. Remember I said that earlier on. So let's see how we can balance that. Now we have 1 hydrogen, we have 2 hydrogen, we have 1 oxygen plus 2 oxygen, that's 3 oxygen. We have 2 plus 1, 3. We have carbon here. Carbon is 2. Here carbon is 1. So if I push 2 here, my carbon becomes 2. My carbon is now 2. It's balanced now. But my oxygen is now 4 plus 1, 5. And this is 2 plus 1, 3. So if I can put, okay, hydrogen is 5 plus 1, 6. So if I put 3 here, I have 6 hydrogen. And oxygen now becomes 3 plus 4, 6. Well, 3 plus 4 is 7. I have 1 here, so I can put 3 here. Oxygen becomes 6 plus 1, 7. Hydrogen is 6, hydrogen is 6, carbon is 2, carbon is 2. Okay, I think we balance now. This is gas. This is liquid, and that's heat. So, combustion, the water, okay, I think water is also gas. Because it's confined, fermentation. Now, this is our first reaction, which is called combustion, which means ethanol turned in oxygen to give us carbon 4 oxide and water. Now let us look at another one, reaction with sodium metal. Okay, number 2. The reaction with sodium metal, ethanol will react with metals in group 1 and 2 in the periodic table to liberate hydrogen gas. So let's take 2 moles of ethanol plus 2 moles of sodium. 2 moles of ethanol, C2H5OH, plus 2 moles of sodium. will give us 2. C2H5O. Sodium will replace this and hydrogen will be liberated. Na plus hydrogen is 2. So this is sodium ethoxide. Ethoxide. So don't forget that. That's what we get. Okay, and don't forget that ethanol is always liquid, and so on. So formation of haloalkanes is another reaction. How do we form what haloalkanes? Reaction with phosphorus pentachloride. So we are going to use ethanol to react with phosphorus pentachloride. Ethanol react with phosphorus pentachloride. So we want to form haloalkanes, which means this halogen will replace this guy. That is it. So now what are we going to have? We have our C2H5Cl. 1 chlorine will replace it. So this is our haloalkane. What is left? We are left with 4 of these. So if I have HCl, hydrogen is out, oxygen is left, hydrogen is out, another one is left. So I'm left with POCl3. So I have my POCl3. So we have been able to form our haloalkane, that is chloroethane. So through our reaction with phosphorus pentachloride. We say ethanol react with phosphorus 5-chloride to give chloroethane with evolution of hydrogen chloride gas. So that HCl, there is a gas. Let's take reaction with phosphorus trichloride. So let's take phosphorus trichloride. 3 moles of phosphorus, of ethanol with, this is trichloride. What do we get? It's still going to give us our 3C2H5Cl. Remember, we have 3 chlorine here. Now, what are we left with? We are left with 3 oxygen, 3 hydrogen, and phosphorus. So plus hydrogen, we have 3 of you. We have phosphorus, which is 1 left, and we have oxygen, which is 3. Okay, I think this is our haloalkane and triazophosphate 3 by oxidation state. If you calculate the oxidation state of that compound, it's 3. Yeah, so this is 6 crossover to 0, 6 minus 3 is 3, so triazophosphate 3 acid chloride. So now we have that. We say ethanol react with phosphorus 3-chloride to give chloroethane, which is that. Now, dehydration of ethanol. Remember in the process where we were carrying out to form preparation of ethanol, we carry out hydration of ethanol, adding of water. So if I want to remove one of its reactions, I want to remove the water, which is dehydration, it will go back to ethene. If I am using ethanol, it will go back to ethene. So when ethanol is heated with excess of corn, H2SO4 to about 180 degree, ethene is formed. So that's just the technicality therein. So let's see. So this is my ethanol. I have my OH, my hydrogen, and hydrogen. Dehydration in the presence of an acid. H2SO4, corn H2SO4. So let me just write it. Corn H2SO4 as a dehydrating agent. So it will lose water. This will be out. So this is what is left. Hydrogen, 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 hydrogen. And of course, our double bond. This is how it works. When we hydrated it in the presence of this, it gave us that. So if you want to remove that water, it will give us like this. So this is dehydration as one of the reactions of ethanol. Then in the preparation of ethanol, we hydrate it to get what we want. We hydrate ethanol to get what we want. Now, oxidation of ethanol. The oxidation of ethanol undergoes 2 stages. In the first stage, it gives us ethanol. In the second stage, it gives us ethanoic acid. So we are going to take ethanol, for example, plus oxygen, give us CH3, C double bond OH. The first stage give us ethanol. That is ethanol. And the second stage we use that, which is our ethanol plus another oxygen. Now give us our carbon double bond is here. The oxygen now comes in, it gives us ethanoic acid. So the oxidation of ethanol undergoes 2 stages, where the first one gives us ethanol, the second one gives us ethanoic acid. Let's look at another reaction, which is esterification. Esterification reaction is a reaction between ethanol and ethanoic acid in the presence of an acid, in the presence of a catalyst, which is H2SO4, to give us ethyl ethanoic if we are using ethanol and ethanoic acid. So let's say that esterification. We have a CH3 C double bond OH. This is my ethanoic acid plus my OHC H2 CH3 in the presence of an acid. Okay, sorry, let's put it here in the presence of an acid. Now, what happened? In this reaction, this will go to give out a molecule of water. And what is left is CH3 C double bond O. This is the O left. Then I continue with the CH2 CH3. This is ethyl ethanoate. Ethyl ethanoate. And this is an ester. They have sweet, fruity smell. In the qualitative analysis, organic qualitative analysis, you're going to see this in the lab where you carry out these reactions, ethanol and ethanoic acid, ethanol and ethanoic acid to form ethyl ethanoate in the laboratory. And if you go to my videos, I have done videos on qualitative analysis and inorganic analysis and qualitative organic analysis. In the organic analysis of the qualitative aspect, where we treated this and food tests, I have videos on them, qualitative analysis. I have one to about 5 or 6 of them. So you can go through them to have your mind refreshed. So this is it. And water, sorry, was my H2O, let me not forget. So I say, when a mixture of ethanol and ethanoic acid is warmed in the presence of corn H2SO4 as a catalyst, the product are water and a sweet-smelling compound called ethyl ethanoate is formed. And that is it. So do not forget what we've done so far about ethynols, that they are compounds that have the hydroxy group attached to a carbon in the S that has a sp that is sp3 hybridized, and we talked about the various classes of alcohols where we have the primary, secondary, and tertiary. Primary having the carbon carrying the OH group is attached to one carbon atom or not. Secondary, the carbon carrying the OH group is attached to two carbon atoms, and tertiary, the carbon carrying the OH group is attached to three carbon atoms. And we talked about the preparation of alcohols, where we undergo hydration, and we also have fermentation process, which in the process of it, we can also carry out the production of illicit gin, which is ogogoro here in the west part of Africa, and so on and so forth in the preparation. We talk about the reaction with phosphorus trichloride and phosphorus pentachloride. And we also carry out dehydration and all those processes, with esterification being the last one. So in all of these, you should not forget, cardinally or most importantly, they have alcohols have a general molecular formula, which is CnH2n plus 1 OH. With that, you can easily determine the molecular formula of any of the alcohols which you're dealing with, no matter how lengthy it may be. And finally, in the procedure for naming alcohols, it has its rules. You have to determine your parent chain being the longest, and you have to also consider the functional group, starting from the functional group, the lowest possible locant from the functional group, and it must be given preference over to the double bond and other subsequent. And in the course of naming, where you follow the rules given to you religiously, I don't see you making any mistake. It is important we know them, because it has to be part of us. You understand? So do have a wonderful time. See you again when I see you. Bye.